Intermediate Algebra, Section 9.2. In this section, we introduce a new type of function, the exponential function. These functions and their inverses, called logarithmic functions, have applications in many fields. The function f of x is equal to a to the x power, where a is a positive constant, a cannot equal 1, and x is any real number. And by any real number, it can be a radical, it can be a decimal, it can be a fraction, it can be an irrational number, is called the exponential function with base a. We require the base a to be positive to avoid imaginary numbers that would result from taking square roots of negative numbers. The restriction a not equal to 1 is made to exclude the constant function f of x equals 1 to the x power, which would result in f of x is equal to 1. This would be just a horizontal line. Like polynomial functions, the domain of an exponential function is the set of all real numbers. There's no reason to restrict the domain. Unlike polynomial functions, exponential functions have a variable exponent. Because of this, graphs of exponential functions either rise or fall dramatically. And let's take a look at an exponential function and graph it. So in this first example, they're asking us to graph f of x is equal to 2 to the x power. Let's set up a table of some values. We'll pick an x and f of x, the result, which is you can think of as your y value. So easy value to start with is 0. 2 to the 0 is going to give us a 1. If we put a 1 in, we have 2 to the first power, which is 2. And as you can see, increasing the values here, we're just going to get higher and higher. Let's see what happens if we have a negative number. 2 to the negative 1. Remember, with a negative exponent, that to avoid it, we drop it to the denominator. And we'll keep on going there. 2 to the negative 2, we'll put 1 over 2 to the second power, or 1/4. Graphing these then, we have the point 0, 1, we have the point 1, 2, the point 2, 4, 3 would be up here at 8, it's headed up towards positive infinity. Our negative 1x resulted in a half, our negative 2x resulted in a fourth, and as we go smaller negatives, it's going to get closer and closer to 0. So if we do a smooth curve to connect this, it'll get ever and ever closer to 0 without actually equaling 0. Note that as x increases, the function values increase without bound. That means they're just going to continue right on out towards positive infinity. And as the x value decreases, the function value decreases, getting closer and closer to 0. The x-axis, or the line y equals 0, is a horizontal asymptote. Asymptote has the meaning that as the curve gets closer and closer to the line, the further we move to the left. It will never cross this line. It's kind of like a force field. Let's take a look at another exponential function. Here they're asking us to graph y equals f of x. In replacement for the function notation is equal to 2 to the negative x. And to help us see how this is different than the last one, anytime we have a negative exponent, we can eliminate that negative exponent, and I'm going to pull this negative x apart into a negative 1 times x. 2 to the negative 1 power is the same as 1 over 2 to the first power, in other words, 1/2 to the x power. So if I clean that up, this exponential function is Ra to the x power. And to graph it, let's set up a table and find some values to get a sense of what this looks like. Starting with 0, we would have 1/2 to the 0 power. Anything to the 0 power is 1. If we let x equal 1, we would have 1/2 to the first power, which is 1/2. X equal 2, we'd have 1/2 to the second power. 1/2 times 1/2 is 1/4. This is going to get ever smaller when our x is increasing. Let's see what happens when we choose negative values for x. So here, putting in a -1, we will have 1/2 to the -1, which means we're going to invert this fraction, which ends up giving us 2/1, or simply 2. X equal a -2 is 1/2 to the -2 power. That means we'll have 2/1 to the second power, which gives us 4. And we can see as our x values get smaller and smaller, our y values are going to get larger. Has a similar feel, only maybe the opposite of what we just looked at. Plotting these points, we have the point 0, 1, we have 1, 1/2, 2, 1/4, and as it gets larger values, this y will get smaller and smaller, closer to 0. Then we had the point -1, +2. We had the point -2, +4. And again, as our x's get smaller, it appears that it's going to continue infinitely in the positive direction. So here is the graph of y is equal to 2 to the -x, or we can think of it as 1/2 to the x power. So let's take a look and see if we can come up with some general observations for exponential functions after looking at those two different graphs. For a greater than 1, the graph of f of x equals a to the x will increase from left to right. The greater the value of a, the steeper the curve. Now we only saw f of x equal to 2 to the x power, and that was a greater than 1. We're seeing as we go from left to right, this is increasing, and that's what we're making our observation. If our a is between 0 and 1, in other words, a rational number, fraction between 0 and 1, the graph of f of x equal to a to the x will decrease from left to right. The smaller the value of a, the steeper the curve. And we only saw one example, and here it is again. We were dealing with our a. If we compare this to the general form of an exponential function, the a was between 0 and 1, and notice it's saying that the graph decreases, has smaller values as we go from left to right. I don't know if you noticed, but both of our graphs had the point 0, 1, and that's our next observation. All graphs of f of x equal to a to the x go through the y-intercept, which is 0, 1. Because of the placement of our x value, putting a 0 in there, any number raised to the 0 power is always equal to 1, and that will give us our y-intercept. Furthermore, we made note of that all the graphs of the form f of x is equal to a to the x have the x-axis as the horizontal asymptote. This acts as a barrier to the graph that will never cross this line. It will never reach y equals 0 in this case, which is y equals 0 is the x-axis. If our exponential function with a greater than 0 and a not equal to 1, the domain of f of x will be all real numbers, and the range of the function is going to be positive real numbers. And if I bring those graphs up again to show you, There are no reasons for restrictions on our domain because we don't have a variable in the denominator. We don't have a variable underneath a radical. So our domain are all x values, but our range, because of this horizontal y equals 0 or our x-axis acting as an asymptote, as the function gets closer and closer, it will get closer, as in this example, as the x value gets smaller and smaller, our graph will get closer and closer to 0, but it will never be an equal 0 to actually put a point on that line. So, looking at our range then, the y values we're using, it's all the positive y values. And so that's why we have here, range will be positive real values. One other note about exponential functions: when a is greater than 0 and a is not equal to 1, the exponential function is a 1-to-1 function. Its graph passes the horizontal line test. And here we have an example of a generic exponential function here. It's passing the horizontal line test, which we use to determine a 1-to-1 function. Because it only contains one point in each one of those horizontal lines, that's proof that the function does have an inverse, and reflecting it about the y equal x line is giving us the intercept, or not the intercept, giving us the inverse of this function.